Hello, so in this video we're going to be now looking at how we can use integration to deal with like motion. So again, the displacement, velocity, or the acceleration of something, right? So previously we used differentiation. So as I remind you, if I remind you here, we can start with displacement and then we differentiate. And that would get me my velocity, right? Then if I differentiate again, then we get acceleration, okay? So we've used this link, this relationship, right? That links these three different quantities together. We can differentiate to get from one to the other. But what about if we want to go the other way? What about if we start with acceleration now, and let's say we want to get back to displacement? We can do that. We're going to do the opposite to differentiation. Well, what's the opposite to differentiation? Hopefully you recall, is integration, okay? So we can integrate from acceleration to get to velocity. Then from velocity, we can integrate back to displacement. Okay. And so again, make sure you have studied and are comfortable with integration from pure. Hopefully you've done integration in pure maths. So we'll be applying integration here, and we'll be using this relationship here. Okay, so that's how we can jump from one quantity to the other by differentiating or integrating. Okay, you need to remember this sort of process here. Okay, how we can get from one thing to the other by integrating or differentiating. Okay, so in this section we'll be practicing integration. Okay, now as a recap again, you should be able to integrate and find areas under curves. So as a recap, if I want to integrate, so x to the power, so if I have a power n, right, x to the power n, if I integrate now, then that would be, I add 1 to the power, so n plus 1, divide everything by that new power. So dividing everything by n plus 1, okay? So I add 1 to the power, then I divide by it, okay? For example, if I have the integral of x cubed, then that would be, x to the, if I add 1 to the power, that'd be 3 add 1, which is 4. Then I divide by the power 4. So that would be a quarter x to the 4. Okay. And then a plus c on the end. Because the idea is if I then differentiate back, well, a quarter x to the 4, that would go to x cubed. Great. But then any number that doesn't have an x in goes to 0. So we need to account for that by having the plus c. Okay. So do not forget that we have a plus c here. For example, as well, if I wanted to integrate, let's say, root t dt, so not x but t, but it's the exact same thing. Different variable, but it's the same process. So obviously we need a power of t. We can't have root t. So firstly, if we convert it as a power, this is the same as t to a half. Right, now we can integrate that power, because then we add 1 to the power, so half add 1 is 3 over 2. Then I'll divide by 3 over 2. Okay, so this is 3 over 2 t to the 3 over 2 thirds to the t 3 over 2 plus c. Okay, because if I divide by 3 over 2, I'm flipping the fraction to get 2 thirds. Okay, and then my plus c on the end. Okay, so hopefully that should be familiar, how we can integrate powers a lot in this way. Okay. Now I also need to be comfortable with areas under curves. We'll be using that as well. So for example, if I have, let's say, the graph x cubed, something vaguely like that, right? Y is x cubed. Okay, let's say we have x is 1 here, and then x is minus 1 on the other side. There. Now we can use integration to find the area under curves between certain points. So let's say between 0, then the origin. Let's say we have this region here. I'll call that region 1, and this region here, I'll call that region 2. Okay. So if I was to calculate the area of region 1, that's going to be the integral of, well, the curve is x cubed. That's what we're going to integrate. And then we introduce these upper and lower limits, right? So it's this area then is between 0 and 1 for x. So x is between 0 and 1. These are my definite limits, right? Then I integrate that to get a quarter x to the 4, as we've seen. We don't need a plus c when we're integrating with limits, right? So then we integrate between 1 and 0. So we substitute the top number. So it's a quarter of 1 to the 4, then take away and plug in the lower number. So it's a quarter of 0 to the 4. So that'll get me an area of just a quarter, okay? So I can say here the area is a quarter, okay? Then if I want to find the area of region 2, that's going to be the integral. Now, for region 2, it's between -1 up to 0. So it's between -1 to 0. Okay, that's my limits here. Again, it's the same curve x cubed. If I integrate that, that's a quarter x to the 4 between 0 and -1. So if I plug in the top number, so it's a quarter of 0 to the 4, take away a quarter of -1 to the 4, and this will get me minus a quarter. Okay, so this is saying the area of the second region here is minus a quarter. Well, how can area be negative? Well, when we're dealing with regions and areas that are underneath in the negative part of the graph, right? So when y is negative, so you see it's underneath the axis, right? That gives us a negative area. However, this is a positive area. So remember, with integration, we can get a negative area and a positive area. Well, the area itself is just a quarter still, right? The area is a quarter, but we get a negative, so we need to flip that to a positive, okay? Because area is a positive quantity. Like, think about shapes. You can't have a negative area in a shape. But you need to pay attention to the sign. If you just integrate, if it's underneath the axis, right? So if it's underneath the axis right here, then it will give me a negative result, which cannot happen because, well, it can happen, but area shouldn't be negative, so we need to pay attention to that, okay? So you need to bear that in mind. So when we integrate to find an area, we might fall into an issue where we get a negative answer, which then we need to flip into a positive. So the actual area would need to flip to a positive a quarter. So area is positive a quarter. Okay, so just pay attention. Okay, again, that will be quite a crucial detail we need to pay attention to. Okay, so that's hopefully that was a good recap. So we're going to look into some examples then. We're going to look at integration. So here I'm told a particle travels in a straight line such that its acceleration is given by a is 6t plus 2. When t is equal to 2, the displacement is 10, and when t is 3, the displacement is 38. So it's asking me to find the displacement when t is 4. Okay, so in essence, what we've got here is we've got the acceleration. Okay, a is 6t add 2, but the issue is they want me to find the displacement. Well, how can we go from acceleration to displacement? Let's have a look at a sort of a little flowchart diagram here. If we start from acceleration and we want to get to displacement, well, actually we're going to integrate, aren't we? Okay, so we're going to integrate. Okay, so if I integrate the acceleration, so the integral of 6t plus 2 dt, because that's my variable t, right? So if I just integrate that expression, I'm going to get, well, firstly 6t here, 6t. Well, t has a hidden power of 1, right? So 6t, then we add 1 to the power to get 2, then we divide by 2. Then plus 2, well, we just add an x on, okay? 2x, okay? And then a plus c, okay? Because then the idea is if we then differentiate this expression back, if we differentiate the expression we get after integrating, we should get back to the original equation, because they're opposites, right? Differentiation opposite to integration. So a plus c will go to 0. Anyway, so hopefully that should you remember that. So if we then just simplify it ever so slightly, well, this fraction here, 6 over 2, would go to 3. So it's just 3t squared add, oh, sorry, not xt, sorry. 3t squared add 2t plus c. Okay, there we are. Now the issue is, what is this plus c here? Well, we can't do anything at the moment. Let's just leave it as it is. Just remember, c is just a constant. It's just an unknown number. It's a placeholder. And so that, what is this expression going to be? It's going to be the velocity, right? V. So remember, acceleration, we're going to integrate, and then we're going to get velocity. But hang on, what's the issue here? What the issue here is, we want the displacement, so we're not there yet. So we're going to need to integrate again, because then velocity integrated gets me displacement. So if I integrate the velocity then, so the integral of v dt, well, that's the integral of 3t squared add 2t plus c dt. And so if I integrate this then, well, 3t squared, well, that would go to 3t cubed, then divide by 3, the new power. And then 2t would go to 2t squared, divide by 2. And then c, well, c, it's just a number, so we add a t on, so ct. Okay, but then we need another constant c. I'm going to call it plus d then. Okay, there. Okay, so when we integrate in this way, we need to add on an unknown constant at the end. So there we are. So if I simplify the fractions, well, 3 over 3 goes to 1, so we just get t cubed. Then 2 over 2 goes to t squared. Then ct plus d. Okay, okay, so now that would be the displacement s. Okay, so now we're there. Okay, so the displacement when t is 4, but the problem is we got these two unknown letters c and d. So in that situation, when we got unknowns, the question will give us information to work with. So here we're told when t is 2 seconds, the displacement is 10. So if I convert that, that's t is 2, s is 10. Okay. Likewise, when t is 3, we're told the displacement is 38. So actually, we've got two different bits of data here, okay, to use. So firstly, when t is 2, s is 10, right? That's what we were given. So if we sub that in, so that means s is 10. It's going to equal 2 cubed, add 2 squared, add 2c, add d. So if I simplify this, this will be 10 is 12 plus 2c plus d. And so therefore 2c plus d is going to be minus 2. And there we are. Okay, well, that's still not enough because it's two unknowns with one equation. But remember, also we know that t is 3, s is 38. So when t is 3, s is 38. So 38 for s, if I substitute it into here then, my displacement formula, 38 is going to equal 3 cubed and 3 squared plus 3c plus d. And again, if I simplify that, I get 38 equals 36 plus 3c plus d. So therefore, I get that 3c plus d is 2. And so therefore, I get these simultaneous equations. So I get that 2c plus d is minus 2. That's my first equation. And 3c plus d is 2. Okay, so then I can solve. Well, actually, I can get rid of d. Right, so if I solve these simultaneous equations, I can eliminate d by just taking these two equations away. Okay, so then 2c take away 3c is minus c. Then d take away d is 0. Then minus 2 is minus 4. So therefore, minus c is minus 4, which means c is positive 4. Then I can sub that into one of the equations. Let's say the second one, right? So therefore 3c, which is 3 lots of 4, add d is 2. So that means 12 add d is 2, which means d has to be minus 10. So there we are. We got our two unknowns. So now if we substitute that into my displacement formula, so S, well, remember S is here, t cubed at t squared, add ct, so it's going to be 4t, add d, which is minus 10. And so there we are. We've got our complete equation for the displacement. And so there we are. That's the whole essence. That's the whole essence, right? We just integrate to get to where we want, and then we might need to sub some information in to find any missing values that we get from the plus c from the integration. Okay, so at this point it becomes fairly smooth sailing, because now if we want the displacement when t is 4, well, now we've got the displacement formula, so now we can just sub t is 4 in. So at t is 4, S is going to be 4 cubed, add 4 squared, plus 4 lots of 4 minus 10, and I've put all that in the calculator. I get 86, and so that's my displacement there. Okay, and then for part B, it then wants the velocity when t is 4. Okay, so now it wants the velocity. Well, actually, we already worked out the velocity. Okay, it's up here. V is 3t squared and 2t at d. C, sorry. Was that a copy? 2t. Okay, there we are. So if I remind you, that's the velocity I got from integrating the acceleration initially, right? But I know what c is. C, we worked that out before. So now we can sub c in to get the complete formula for v. There we are. So that's my velocity. So again then, when t is 4, the velocity is going to be 3 lots of 4 squared, add 2 lots of 4 plus 4. And so that will get me at 60, okay, and that being meters per second, okay. And so there we are. Okay, so again, because we found the displacement, you don't need to differentiate then to get back to the velocity, because we found the velocity anyway. So I'm just reusing the working to not do any more working than I need to do. Okay, so you didn't need to do that. You didn't need to differentiate the displacement to get the velocity, because we already have it. Okay, it was here. Okay, so there we are. So we've got this question here then. So here we're told a particle is moving on the x-axis. At time t0, the particle is at the point where x is 5. So x is going to be my displacement, right? Okay, and so initially the displacement is 5. The velocity is given by this expression here. So v, the velocity is 6t take away t squared, okay? And then it wants me to find, for part A, an expression for the displacement. Well, again, we got the velocity, but it wants me to find the displacement. So I'm going to need to integrate, right? So if I integrate my velocity, so 6t minus t squared dt, well, if I integrate 6t, well, that'll go to 6t squared, because the hidden power 1, I add another 1 to get 2, then I divide by the new power 2. Then minus t squared will go to minus t cubed, then I divide by 3. Okay, again, divide by the new power 3 here, by adding 1 to the power. Okay, and then I have my plus c on the end. Okay. And then if I simplify the fractions down just a little bit, well, 6 over 2 goes to 3, so 3t squared, then minus a third t cubed plus c. Okay, so that's my displacement then, f, or x, sorry, they used x here, okay. Usually they call it s or x, okay, for displacement there, okay. But I need to find what my plus c is, but actually I've got this condition here. I'm told when t is 0, the displacement is 5. So it starts at 5. So that means when t is 0, x is 5. So there we are. If I sub that in. So then x is 5. That means when t is 0. So 3 lots of 0 minus a third lots of 0 plus c. Therefore 5 is c. Okay. And so simply x is then 3t squared minus a third t cubed plus 5. And there we are. That's my expression there. Okay, then in part B, it wants me to find the distance of the particle from its starting point when t is 6. Right, so we can also then consider the distance apart an object moves. Okay, so how are we going to approach this? Well, firstly, probably a good idea. You might be thinking, well, wow, I got my displacement formula. Let's sub in T6. Let's do that then, okay? So if I sub T6 into X, my formula X here, then that means I'm going to get X is going to be 3 lots of 6 squared minus a third lots of 6 cubed plus 5. If I put that in the calculator, I get 41. Okay, 41 meters. However, this is not my final answer because this tells me the displacement from the origin when x is 0. Okay, so if I draw a little diagram, what we've got going on is from the origin, right, when t6 all the way over here, then the distance from the origin, right, is 41 meters. But that's not from the starting point. Our starting point, remember, we're told initially the displacement is 5 meters. Okay, this is 5 meters away from the origin when it's 0, right? So this is when t is 0. So initially we're 5 meters away from the right? The point 0. And then and then 41 meters is the displacement from O, okay? But that's not what the question wants. The question's asking for the distance from its starting point, okay? From its starting point is here. So actually wants this distance here from its starting point at T0 until T6. So this distance here, well, how can we work that out? Well, the distance, hopefully you can see then, if we consider the what we've got here, the distance that we want is going to be 41 take away 5. And so that leaves me with 36 meters there. And that is my answer. Okay. Very, quite a malicious question, I feel like. Vast majority of the time, your starting displacement will be 0. Kind of makes sense because if you're starting, you've not moved anywhere yet. But I guess this question tried to throw you off by starting somewhere else, okay? And so there we are. That's the actual distance they're after there, okay? Right. So we've got this question here, and again, this one will also throw you off, I think. I'll get to that though. But here we're told a particle travels in a straight line. After t seconds, its velocity is given by v is 5 minus 3t squared. Find the distance travelled by the particle in the third second of its motion. Now, this is what I think is going to cause the issue, in the third second of its motion. Okay, so they're giving me the velocity, which is 5 minus 3t squared. They want me to find the distance, so that's to deal with displacement and stuff like that. So again, I've got the velocity, but I want the displacement. Now, there are two ways you can approach this. I did the first method kind of previously when I just substituted stuff into the displacement formula. I'm going to show the other method to do with integrals, okay? So recall that with a velocity time graph, again, let's say we have a velocity time graph. Think back to earlier on in the course. A velocity time graph looks a bit like this, right? We've seen velocity time graphs like that. Now, what does the area under velocity time graph represent? The displacement or the distance if it's positive, right? So the area under the graph, under a velocity graph, that represents displacement, right? So actually, I don't necessarily need to find the displacement if I'm given the velocity, because what I can do instead is consider the area under the velocity graph, which I can do by graphing this equation here. And actually, what I'm going to look at is I'm going to sketch the graph for now, but I'm going to show a method later on where you don't even need to sketch the graph, okay? But let's just sketch the graph now just to illustrate my point, okay? So let's sketch this graph here, this velocity graph, but it's going to be a quadratic. So firstly, it's going to be a negative quadratic, so it's going to have a frowny shape like this. And then if we find our roots, right, that's going to be setting v to 0. So then we get the equation 5 minus 3t squared is 0. Therefore 3t squared is 5. So t squared is 5/3. Therefore if I root both sides, I get t to be 1 point plus or minus 1.29. Actually, I'll give an exact form. T is plus or minus root 15/3. Okay, or as a decimal, that plus or minus 1.29 to 2 decimal places. Okay, and so then these are my two roots. Right, again, I emphasize roots. So if I can then use this to sort of sketch my velocity graph. So again, I've got t against the velocity v. Again, it's going to have a negative frowny shape like this because it's a negative quadratic. And it passes through plus 1.29 and minus 1.29. There we are. So it's going to have this sort of shape. There, okay. Right, so that's my velocity time graph. But they want me to find the distance travelled in the 3rd second of its motion. So I need the area under the graph corresponding to the 3rd second. Now, in the 3rd second, I think the best way to kind of visualise exactly what time frame they're talking about, what values of t we need to consider. Well, if I just consider a little number line here, right? T0 initially starts off at 0, right? Then if I go up to T's 1, this is actually the 1st second. Okay, that makes sense. Between T0 and T's 1, that's 1 second in between. So that's the 1st second. Then when T's 2, then that's the second second, right? Then when T's 3, up to T's 3, right? Then we get the 3rd second. Okay. So the values of t we need to consider in the third to make up the 3rd second is between T's 2 and T's 3. Okay, it wouldn't just be T's 3 and then that's it. The 3rd second is the time frame between T's 2 and T's 3. Okay, hopefully it made sense. Hopefully that number line has kind of helped with that. Okay, because I think that could throw a lot of people off. Okay, so as we discussed then, if we want the 3rd second of the journey, that would be between T's 2 and T's 3. So if I consider T's 2, if I move that here, 1.29, T's 2 there, and then T's 3 here. If I extend the my graph then downwards, I'm going to want the area here, right? Literally between T's 2 and T's 3. That area will correspond to the distance in the 3rd second between T's 2 and T's 3. Okay, and so that corresponds to finding the area under this graph between T's 2 and T's 3. Okay, and so again, as I remind you, the graph is v is 5 minus 3t squared. Right, so I'm going to integrate the graph. So the distance will be the area under the graph between T's 2 and T's 3, right? So it's going to be the integral between 2 and 3 of the graph v, which is 5 minus 3t squared dt. So at that point we can compute distances that correspond to areas under a velocity graph by working out definite integrals. Okay, so if we work out this integral again, that would be then 5t take away 3t cubed over 3 between 3 and 2, and then I can simplify that a little bit. because then that'll go to 5t minus t cubed between 3 and 2. If I just simplify the fraction down, then if I sub in 3 first, that'd be 5 lots of 3, take away 3 cubed, and then take away 5 lots of 2, take away 2 cubed. If I work all that out, I get negative 14. Okay, well hang on, why is it negative? The area is saying it's negative. But actually, remember what I talked about at the start. This area here, this region, is underneath the axis. It's in the negative part of the graph, right? So actually, the area is going to be negative. The integral will be negative, so the area needs to be flipped into a positive. So actually, the distance or the area is just positive 14 meters. So it's 14 here. And that is the distance they travelled in the 3rd second. Okay. So yeah. Okay. So we can also use integrals to work out areas. Okay. And I'm going to look at in probably the next example how we don't even need to sketch the graph. Okay. We can just dive right into the integration. Okay. Right, and so there we are. Hopefully you understand how we worked out with the integral, and also why we got a negative answer, so we need to flip it into a positive, because it's a positive quantity, right? Area and distance are positive quantities. Okay. Now if it asked for the displacement would just be minus 14. That'd be correct. Okay. But remember, distance is positive displacement. So distance is always positive. So we need to flip that to a positive. But the displacement can be negative. So it would be minus 14. So I'll make a point here to say the distance is 14, but the displacement in the 3rd second would be minus 14. So it might be going backwards by 14 meters, right? In the negative direction. Okay. But it wanted distance here. The question wanted distance. So I need to make it positive. Right. Okay. So let's have a look at this question then. So here we're told a particle is moving in a straight line at time t seconds. The velocity it's given by v is 6t squared minus 51t at 90. When t is 0, the displacement is 0. Okay. Find the distance between the 2 points when p is at rest. Okay. Rest is when the velocity v is 0. Okay. Now, in this chapter, like in all the questions we'll be looking at, we're going to need to consider the velocity 0 when it's at rest. It's going to be quite a crucial thing we need to consider. So we need to consider when it's at rest. So firstly, well, we got given the velocity. Let's just set it to 0, right? So then that means 6t squared minus 51t at 90 equals 0. Then we just solve. So then t is 51 plus or minus the root of minus 51 all squared minus 4 lots of 6 lots of 90 over 2 lots of 6. And so if I put all that in the calculator, I get t is 6 or t is 5 over 2. And so those are my 2 points right there. Okay. Right. So I need to find the displacement between these 2 points in time. 6 seconds and 5 over 2 seconds into the journey, right? So the idea is, again, if I have to do a little sketch, we start at this starting point, say here. And so we want to find the distance when we're 5 over 2 seconds in, and then when we're 6 seconds in. Okay, we want this distance here. Okay, so how are we going to go about doing that then? How are we going to go about doing that? So, okay, so again, there's 2 main methods. I'll do both here then. Okay, so the first method is we could just use the displacement formula, okay? Now this method is a bit trickier because, as you know, displacement and distance are not the same. If we want the distance, that's different. Displacement, we need to be very careful because it might cancel out some of the distance because it could be negative, right? For example, again, if we again start here at 0, then let's say we walk 4 meters forwards, then 4 meters backwards. Well, yes, the distance will be 8 meters because we physically walked 8 meters front and back, but the displacement is 0 because it's only relative to where we start. So if we returned back to where we started at O, then we've not moved anywhere really, so the displacement will be 0. So the 4 meters cancel each other out because they're going opposite directions. So that is the main difficulty with these questions, is how sort of delicate displacement is, because it could be negative, it could cancel out. So we need to pay very special attention. But okay, how are we going to deal with that then? So firstly, we need displacement, right? So we've got the velocity. So we need to integrate to get the displacement. So if we integrate the velocity, which is 6t squared minus 51t at 90 dt, if we integrate all that, well, firstly, 6t squared will go to 6t cubed over 3. And then minus 51t will go to minus 51t squared over 2. And then 90t, oh no, just 90. Then 90 will just go to 90t. We add a t on, right? And then we also add on a plus c, okay? So if we simplify this a little bit to simplify the fractions, well, 6 over 3 goes to 2, so 2t cubed minus 51 over 2t squared at 90t plus c. Okay, this is my displacement S then, but of course the issue is here, I've still got an unknown here, c. So I need to find this plus c. Well, actually the question has given me some details. When t is 0, the displacement is 0. Okay, so that means when t is 0, S is 0. So I can sub that in. So that means 0 is equal to basically 2 lots of 0 cubed minus 51 over 0 over 2 lots of 0 squared. Add 90 lots of 0. Add 3. And basically all the zeros cancel out. So I just get C is 0. Okay, so therefore my final formula is S is 2t cubed minus 51 over 2t squared add 90t. Okay, so then, right, that's my displacement formula, cool. So I want to find the distance between the 2 points that I've found, right? Which, the 2 points here, at these 2 time values here. These 2 points in time. So firstly, well, we want to find the distance, probably a good idea to find the displacements of them then, right? So I'm just going to sub these 2 values into the formula. So at t6 firstly, S is going to be 2 lots of 6 cubed minus 51 over 2 lots of 6 squared, add 90 lots of 6. And so if I put all that in the calculator, I get 54, okay, meters there. And then when t is 5 over 2, yes, 5 over 2 then, S it's going to be 2 lots of 5 over 2 all square, all cubed, minus 51 over 2 lots of 5 over 2 all squared, add 90 lots of 5 over 2. And so if I put that in the calculator, I get 775 over 8 meters. Okay, right, and so there we are. Now, of course, the tricky thing is we want the distance between these 2 points. So again, the idea is that it can be a bit tricky because we've got displacement here. So the way we probably want to tackle this is, again, draw just a very rough little diagram of the points we've got. So if I draw a little line then, kind of like a number line, right? Again, we start here. This is my starting point O. And so then if I add on these two distances, by the way, this distance is as a fraction, as a decimal, sorry, 96.875 meters. Okay, so what's interesting is initial when t is 2.5 seconds, 5/2, it travels a further distance than 6 seconds down the line. So we've got this idea where it moves forward and moves backwards. Okay, so it makes it a little bit tricky, but again, if we just then sketch these two bits of information, so 54 meters and 96.8 meters at these two time points. So firstly, when t is 5/2, it's 96 meters. So let's say t is 5/2 over here. At this point in time, the distance from the starting point, right? The distance from the starting point is 96.875 meters. Okay. And then when t is 6, then it's now at 54 meters. Right, that's the displacement. That's from the starting point again, right? So the distance from the starting point after 6 seconds is 54 meters. So 6 seconds is going to be somewhere here, right? So this distance is going to be 54. Okay, but the question wants the distance between the 2 points. So this distance here, right? Well, how are we going to work that out? Well, again, now that I've drawn this little diagram here, just plot in the distances at the 2 points from the starting point, right? Hopefully you can envision how we can get the distance. So the distance is then going to be this 96.875 take away 54. And so if I do that, I get 42.875 meters, or 42.9 meters to 1 decimal place. And so that's my distance there. Okay, so that's one method. Okay, you can integrate to get the displacement formula, then you can sub your values in, and then do a little sketch if it helps to find out exactly how to get the distance you want. Okay, alternatively, we can use integrals to work this out. Okay, to work out distances. Okay, by the way, this is a very common exam question. I've seen it probably every AS mechanics past paper, where you need to work out the distance between certain points. Okay, so this is an important skill here. So okay, the second method is using integrals. Okay, now what we're going to be utilizing instead of the displacement formula is the fact that the area under the velocity graph is the distance, right, or the displacement depending on whatever, right? So we're going to be utilizing that fact here. So we're going to be using integrals of the velocity equation here. Now again, I don't need to sketch the velocity graph, because what I can do instead to play it safe, again, this method I think is the safer route, and the route that I'll be taking for these questions mainly. So what we're going to be doing is, instead, we're going to integrate the velocity, but where we're going to integrate it between, again, we've got these two limits, these two numbers, right, on the top and bottom. So if we want the distance between the 2 points, right, well, actually, this is actually quite simple then. The distance between the 2 points is just going to be the integral between the first point, which is 5/2, so the lower one, right, so 5/2, and then the next point, 6, okay, and that's it. Okay, that will give me the distance. Now it might be negative, but then we just flip it to a positive. Okay, so if I then integrate the velocity curve, because remember it's the area under the velocity graph that gets me the distance, right? So if I integrate the velocity graph, 6t squared minus 51t add 90 dt between these two limits, between the 2 points here, because it wants me the distance between the 2 points. So then if I work that out, well then that would be again, if I integrate that, that'd be 6t cubed over 3, which will go to 2t cubed. And then minus 51t will go to minus 51 over 2t squared. and then 90t, okay? And then we don't need the plus c because it's definite integration. It will go away anyway. Again, we should be comfortable with that from normal maths integration. So this is definite integration now with limits, with numbers involved. And again, it's between 6 and 5 over 2. So either way, you're going to have to integrate. There's no getting away from that. You're going to, either method, you're going to have to integrate the velocity. But the ways we do it are slightly different. Okay, so now we just work out this sort of integral here. So again, we're going to sub in the limits. So 2 lots of 6 cubed minus 5 over 2 lots of 6 squared plus 90 lots of 6. Then I'm going to take that away. There we are. So then we're going to take that away from the upper limit at 5 over 2. So 2 lots of 5 over 2 all cubed minus 51 over 2 lots of 5 over 2 squared plus 90 lots of 5 over 2. And so if we put all that in the calculator, we get minus 42.875 meters. Okay. Well, actually, isn't that the exact same answer we get? But it's just negative, right? So we got minus 42.875. Right, but our actual answer from the first method was positive. Now that's fine, because then we flip it to a positive. What this answer is saying, because it's negative, is underneath the axis, so it's in the negative part of the graph. So to get the distance, we make it positive. Okay, so the distance will be positive 42.9 meters to 1 decimal place. And there we are. So you could use either method, okay? The integrals method is safer, and probably generally the better method, I think. And you don't have to worry about the plus c, because again, with the first method here, we needed to spend a where were we? We needed to spend some time to work out what the plus c was, okay? But you don't need to worry about that with the definite integral method. But you can use either method you want. So either you could just find the displacement values by finding the displacement formula, then doing a little graph to work out the distance you want, or you could just integrate and just flip a negative to a positive at the end if necessary. But there we are. Okay, so we've got this question here then. So here we're told a particle is moving on the x-axis at time 2 seconds. The velocity, again, is given by 4t take away t squared. Okay, in the direction of x increasing. At time t0, p is at the origin. Okay, so the displacement is 0 again, right, if it's at the origin. So for part A, once we find the value of x at the instant when t is greater than 0, okay, but p is at rest. That's the key part. That's the key part here. That means the velocity is 0. Okay, well actually, let's just consider that then. Let's set v to 0. Then that means 4t take away t squared is equal to 0. Then we can factorise the t out to get 4 minus t equals 0. So we get t is 0, or t equals 4. But obviously it told me t is greater than 0 at this point, so t can only be 4. And there we are. But that they didn't ask me to find the time when it's at rest. It asked me to find the value of x. Now x again is the displacement. Okay, so we need the displacement, but we've got the velocity, so we're going to need to integrate, right? So we're going to need to integrate this. So if we do that, that'll get me, well, 4t will go to 4t squared, then divide by the power 2. Then minus t squared will go to minus t cubed, then divide by 3. And then add my plus c on at the end. And that's my displacement x. Okay, again, it's either x or s they use normally. So then we can simplify it a little bit to help us out. So so 4 over 2 goes to 2. So that'd be 2 t squared and then minus a third t cubed plus c. Okay, but we need the plus c. So again, pay attention to any information they tell you. Well, here we're told at t0, p is at the origin. That means x is 0. So the displacement is 0. So that means when t is 0, x is 0. So therefore 0, if we sub that in, that's 2 lots of 0 squared minus a third lots of 0 cubed plus c. Therefore c is 0. So my complete expression for x is going to be 2t squared minus a third t cubed. And so there we are. And so to find the value of x then when it's at rest, in other words, when t is 4 then, I sub that in then. So sub t is 4 into x. So therefore I get that x is going to be 2 lots of 4 squared minus a third lots of 4 cubed. And that will get me 32 over 3 meters. Okay, the decimal isn't quite nice, so I'm just going to leave it as a fraction there. And so there we are. That's the value of x then. Then for part B, it wants the total distance travelled by p in the interval 0 to 5, so between t0 and t5, right? In the first 5 seconds. Okay. So the total distance then, well, again, we can use either method. We can use 2 methods of substituting into the displacement. I'll tell you what, I'm going to do both again. I'll do both methods, okay? But this time I'm going to start with the integral method first. So I'm going to say method 2, the integral, but I'm going to do that first, just to make it match with the last example. So if I want to compute this by setting up an integral, okay, well, the total distance between 0 and 5. So we ultimately want to integrate between 0 and 5, right, of the velocity. So the velocity is 4t squared. No, sorry, 4t take away t squared here, right? So I'm integrating the velocity between the limits, the values of t between 0 and 5. But the issue is, if I just integrated straight up from 0 to 5, the issue is the velocity graph might go underneath like this. So say, let's say 5 is here, then they've got the portion of the graph that's a positive, that's above the axis, then it goes negative here. What would happen is, if we just did that all in one go, these two areas would cancel each other out, the negative and the positive area, right? That would net to 0 or something like that. So, but obviously the distance, we want to actually account for all the individual areas and add them up. That's what we want to do, right? So we can't just skip it to do 0 and 5 in one go. What we need to do is split up the integral into the points where it crosses the axis, so here and here, right? Now actually, when it crosses the axis, so again, this is a velocity graph because the area under velocity graph is the distance. Well, when it crosses the axis here and here again, that's when v is 0. So actually, what we can do to split up an integral is we're going to split it up to when the velocity is 0. So when velocity is 0, we worked that out in part A, right? When it's at rest. When v is 0, we discovered that t is 4. Right, so what we're going to do is actually we're going to split up the integral from 0 to 5 by the times it's at rest. So we're going to start at 0, then we're going to go up to 4, okay, of blah blah blah. Then we're going to add on the integral from 4 to 5. That's my end point. That is the idea of this method. We do the integral in this way by putting the limits in, but we split up the limits to when the velocity goes to 0. So we need to find the times when the velocity is 0, then integrate and then split up the integral in that way. So the distance that we want is going to be the integral between 0 and 4, right, of the velocity. So the velocity was 4t take away t squared. And then add the integral of 4 to 5 of 4t minus t squared dt as well. The idea is I expect one of these integrals to be negative. I don't know which one, it doesn't matter. Again, if I sketch the graph, I'd be able to spot which one, but I don't need to sketch the graph. So I need to compute these integrals separately, and then if one of them turns out to be negative, then I flip that to a positive. Okay, that's the whole idea. So I'm going to compute this separately. So firstly, the integral of 0 to 4 of 4t take away t squared dt. Now, this might seem like a lot of work, but actually you'll realise once we work out the first integral, we can kind of reuse that into the next one, because it's the same integral, right? So if we work out the integral of 4t take away t squared, that would be 4t squared over 2, then minus a third t cubed, right? So that'd be 2t squared, right? Take away third t cubed between 4 and 0. So if we sub the limits in there, that'd be 2 lots of 4 squared minus a third lots of 4 cubed. Then plug in 0, then take away when I plug in 0. So 2 lots of 0 squared minus a third lots of 0 cubed. Well, actually, this is quite nice because this would all go to 0, right? The second part. But if we work this out, then we will get 32 over 3. Okay, that's positive, that's great, but then we need to consider the next integral here. Okay, and I'm going to expect then, if that was positive, then the next integral might be negative. So secondly then, we're going to integrate between 4 and 5. And so doing that, again, it's the same exact same integral now. Don't need to integrate it again. We can just reuse it. So that'd be 2t squared minus a third t cubed between 4 and 0. And so doing that will get me 2 lots of between 5 and 4. There we are. So 2 lots of 5 squared minus a third lots of 5 cubed. Then I'm going to take away and then plug in 4. Okay, so if I put all that in the calculator then, yes, I get negative 7 over 3. There's my negative. So this part of the graph, so the velocity graph between 4 and 5 must be underneath, okay? So it's a negative area. So actually therefore the distance then, well, the distance is going to be these two results added. So 32 over 3. But then we need to flip this to a positive, so it's going to be plus 7 over 3. And so that is the, so that if we add that up, we get 13, and that'd be meters, and there we are. So you can see the issue there was, if I was to integrate just from 0 to 5 in one go, what would actually happen was we would get 32 over 3 take away 7 over 3. So if we did 32 over 3 take away 7 over 3, that would be 25 over 3. That's different to 13, right? So we need to make sure to account for when the area becomes negative, which is why we split up the integrals in this way. So there we are. Okay, so you can work it out in this way. There. Alternatively, again, we can just use the displacement formula. So this is method 1 now. Use displacement formula. Now, actually, you might consider opting for this one because we already found out the displacement in part A, right? So we've done some of the work already, right? Here, we've got the displacement formula already. for us to use. Okay, so x is 2t squared minus a third t cubed, wasn't it? Yes. Okay, so we got that pre-used. Okay, that's great. We already know that out. We already have that one, right? So again, then, if we want the distance between 0 and 5 here, it's going to be the same idea. Again, the same idea is we're going to need to split this up into the times when it comes to rest. So when v0, again, it's at t0 and t4. So we're going to need to substitute in. Well, firstly, we're going to need to sub the endpoints in. So t0 and t5, but also then t4 as well. Okay, because that is when the velocity is 0. Okay. So if we do all of this then, again, it's just a substitution exercise. So I'm going to substitute that into x. So firstly, at t0, x is going to be 2 lots of 0 squared minus a third lots of 0 cubed, which is 0. Okay. Then when x is 5, that's 2 lots of 5 squared minus a third lots of 5 cubed. And so that will get me 25 over 3. Okay, then when t is 4, x is going to be 2 lots of 4 squared minus a third lots of 4 cubed. Okay, and so I get 32 over 3 there. Okay, and so then if we if we want the distance from 0 to 5, so again, if I draw a little diagram then to represent what's going on, a little number line, if you will, where again initially we start here. This is my start at O or 0, whatever you want to call it. That's my starting point, and then t0, it's 0 meters, so that's great. So it starts at 0. Cool. Then when t is 5, it's 25 over 3. And then when t is 4, it's 32 over 3. So firstly, if I then plot t is 4, it's going to be over here somewhere, right? That the distance from the starting point, because this is displacement, right? It's the distance from the starting point. That distance is 32 over 3 meters. But then when t is 5, it's a bit less than that. It's going backwards after t is 4. Then the distance from the starting point is now just 25 over 3. So when t is 5, the distance from O, the start, is now 25 over 3 meters. Okay. So the idea is now that I've got this sort of diagram, the idea is, well, actually, if I start at my starting point, well, firstly, I go to t is 4. So I travel forward by 32 over 3 meters. Then from t is 4, I then travelled this distance, right? Where was it? This distance here, right? From t is 4 to t is 5. I then travelled this amount of distance to get from t is 4 to t is 5. But I don't know that distance, right? What is that distance going to be? Actually, if I move this up a little bit, up here, right? So what is this distance here going to be? Because that's the idea then. So we start from, again, the starting point. Then we go to t is 4. So that means, essentially, we go forwards by 32 over 3 meters, right? And then from t is 4, then we go backwards to then this point t is 5. So basically we're going to need to find this distance here. Well, actually then, if we also know this distance then surely the distance from t is 4 to t is 5, that's going to be 32 over 3 take away 25 over 3. So if we work that out, that's going to be 7 over 3 meters. So this distance here is 75 over 3. No, 7 over 3. There. So the distance they travelled then from 0 to 5 seconds. Well, again, we start here. Again, the idea is, once again, we start from O, then we move forwards by 32 over 3 meters up to t is 4. Then from t is 4, we move backwards a distance of 7 over 3 meters up to t is 5. So overall, we travelled 32 over 3 meters, then a further 7 over 3 meters backwards. Okay. Again, drawing a diagram will really help visualize this, because displacement can be quite tricky to sort of visualize, right? And so therefore the total distance then for between 0 to 5 it's going to be 32 over 3 add 7 over 3 which is 13. And hopefully you remember that's the exact same answer we got at the end of the integration method. And so there we are. So there are two different methods then, right? You could either then in this case find the displacement formula, then sub the values in that you need, and then draw maybe a little diagram if it does help to spot the actual distances you need to consider, and then you just go from there, right? But this, I think this is quite a bit trickier, because again, displacement I think is quite a tricky concept to just kind of visualize how exactly where things move, because again, displacement isn't that straightforward, because displacement can cancel. If you go backwards, it might mess it up, because it might cancel out some of the distance. So you need to basically scrutinize it and consider it from one point to another, okay, like we've done here. Okay, so a diagram might help to visualize that, but there are two different methods there. But I think the integration method is a bit more straightforward. It might take a little bit longer, it depends, but those are the two methods, right? Okay, so we've got this question here then. So here we're told a fixed point O lies on the straight line. A particle moves on the straight line such that at time t seconds, the velocity is given by 15 take away t squared take away 2t. Okay, then in part A it wants me to verify that P comes to instantaneous rest when t is free. Well, okay, two things. Firstly, rest again means the velocity is 0. But in part A, it wants me to verify. That means I don't need to necessarily solve this. I just need to substitute it. I need to check the answer works. So I just need to substitute the answer in. So if I sub t's 3 into v then that means v is going to be 15 take away 3 squared, take away 2 lots of 3. And hopefully, put that in the calculator, you should get 0, which means it comes to rest. You do indeed. That's 0. So therefore, comes to rest at t's 3. And there we are. Then in part B, it wants me to find the magnitude of the acceleration when t's 3. Okay. So again, we got velocity. So he wants me to find the acceleration. Well, how do we go from velocity to acceleration? You need to remember it's differentiation, not integration, okay? So remember this here, velocity, to get to acceleration, we need to differentiate. If we want to go from acceleration to integration, to velocity, then it would be integration, okay? But to get from velocity to acceleration is differentiation. So we just need to differentiate v here. Doing that, if we differentiate v, we get the acceleration to be, well, 15 goes to 0, then minus t squared goes to minus 2t, and then minus 2t goes to minus 2, and there we are. So then the acceleration when t is 3, I'll just sub t is 3 in, right? A is going to be minus 2 lots of 3, minus 2, so that would be minus 8 meters per second. That's the acceleration, but it wants me then, keyword, to find the magnitude of the acceleration. Now the magnitude again is the positive version, right? So the magnitude is just going to be positive 8 meters per second. So the magnitude is only talking about the physical number. Okay, it doesn't pay attention to the sign, just the physical number. So here 8. Okay. So there we are. Okay, then in part C, again, very common exam question. They do like to ask to find the total distance between certain points. So here it's asking me to find the total distance between 0 and t and 4. So when t is between 0 and 4. Okay. Now again, if I then just do the integral method, if we will, so to find the distance, well, again, you would expect the distance to be between, if it's between 0 and 4, you'd expect to integrate between 0 and 4, right, of the velocity, right? So the velocity is 15 minus t squared minus 2t. However, we need to also pay attention to the fact the area might become negative throughout. Okay, the graph might dip underneath the axis, so the negative area could cause issues. Now remember, it will only turn negative here, at least with these sort of functions, when v sets to 0. So when it crosses the axis at v0. So if we just solve v0, right, if v0, then that means 15 take away t squared, take away 2t0. Now in part A, we know that t is 3 is one of the solutions, but if we just solve that, right, I'm not even going to put the formula, I'm not going to write down the formula, I'm just going to solve it on the calculator. So 15 minus t squared, minus 1 minus 2. So if we solve the equation when we set velocity to 0, the time when the v0, we get t is 3, which is one of the solutions in part A, right? Or t is minus 5. Obviously, we can't have t is minus 5, so t is 3 only. It's the only solution there. So we only need to split this up. We need to split this up from 0 to 3. And then from 3 to 4. Okay. So the idea is then, if we split it up in this way, one of these integrals will be negative, so we need to make it positive, okay? So, okay, if we work these two integrals out separately, firstly, between 0 and 3, while we integrate this, well, 15 goes to 15t, then minus t squared goes to minus t cubed over 3, then minus 2t goes to minus 2t squared over 2. Between 3 and 0, we can simplify this to get 15t, take away a third t cubed, take away t squared between 3 and 0. And so then we sub in our limits. So it's between 15 of 3 minus a third lots of 3 cubed minus 3 squared. Then plug in 0. And so doing that, we get 27. Okay. Okay, so then if we work out the next integral, that's between now 3 and 4 then of the same function, because it's the velocity, right? So if we work that out again, it's going to be the exact same integral. So 15t take away a third t cubed, take away t squared, but now it's between 4 and 3. Okay, so just the limits change. Okay, so if I plug in my limits, I'll get 15 lots of 4. Okay, so I've subbed in my limit, so if I just put that in the calculator then, I get minus 13 over 3. So there's my negative area, right? So therefore, the total distance then, we need to add these two individual parts up. So 27, okay, that's great. But then we need to make this minus positive, so I'd be adding 13 over 3. Okay, so I add the two individual distances together to get the total distance to be 94 over 3 meters. And there we are. Cool. So we're told a particle moves on a straight line such that after at time t seconds, the velocity is given by v is 7 minus 2t times t plus 2. Okay, so in part A, it wants me to find the value of t when p stops accelerating. Okay, so when it stops accelerating, the acceleration is 0, right? Now the issue here is, the two issues is, we have velocity, but we want acceleration. Well, what you should know is we're going to differentiate. But there lies my second problem. I can't easily differentiate this at the moment because they're not just nice powers of t. We've got some multiplication. We've got these brackets. So simply what we're going to do is to make it differentiable, right, use the power rule. We're going to just expand the brackets. So if we expand, we're going to get 7 times t is equal to t, then 7 times 2 is plus 14, then minus 2t times t is minus 2t squared, and then minus 2t times 2 is minus 4t. And then if we just simplify this, v is minus 2t squared, and then 7t minus 4t is plus 3t plus 4t. Now we can differentiate to get the acceleration. So therefore, A, the acceleration, if we differentiate, well, minus 2t squared will go to minus 4t, and 3t will go to plus 3, and then the plus 14 at the end, it's just a number, so it goes away to 0. And that's my acceleration then here. Okay, so then the acceleration, if we set A to 0, so at A0, then minus 4t plus 3 equals 0. Therefore, if we solve this for t, we get 4t is 3. So t is 3 over 4. And so there we are. That's my value of t there. Then in part B, then it wants the distance of the particle p from the starting point O at the instant when p changes its direction of motion. Okay. So what does that mean, change its direction of motion? You might be able to guess based on the other questions, that's when v is 0. You might guess that, you'd be right. It's the same as it being at rest, but why? Because if it's changing its direction of motion, so let's say it's moving forward, then we're saying at this point here, then it's going to go the other way. Now, for that to happen, if there's a change in direction, the velocity has to come to rest, so it's 0, right? So when the velocity goes from positive to negative because it's changing direction, at some point, at that point in time, the velocity has to be 0 in the middle between positive and negative, right? If that makes any sense? So that's the same as setting v to 0. Okay, so now that we've established that, it might make things a lot easier. Okay. So you want the distance when the velocity goes to 0. Well, actually, we have the velocity here, right? So if v equals 0, then that means 7 minus 2t and t plus 2 equals 0. So we get that 2t equals 7 or t equals minus 2. But obviously we can't have that because that's negative. So then we get t is 7 over 2. And that's my only solution there. So in other words, we want the distance at the point when the time is 7 over 2. Okay, from O. Okay. Well, we want the distance then. We're going to need to compute the integral from 0, right? Because it starts from O at 0 until when it goes to velocity 0. So in other words, from time is 0 at the start until when the time is 7 over 2. So we're integrating the velocity from 0 to 7 over 2, right? And the velocity, again, if I remind you, is minus 2t squared at 3t plus 14. dt. So we just then we just compute this integral, right? So doing that, well, minus 2t squared will go to minus 2t cubed over 3. Then 3t will go to 3t squared over 2. And then 14 will go to 14t. And there we are. And that's between 7 over 2 and 0. Okay. So working this out, if we just simplify the fractions to make it nicer, it's minus 2/3 t cubed plus 3 over 2 t squared plus 14t. Okay, so then if we plug in our upper and lower limits, so that would be minus 2/3 of 7 over 2 cubed, add 3 over 2 of 7 over 2 squared plus 14 lots of 7 over 2. Then we take away minus 2/3 of 0 cubed plus 3 over 2 of 0 squared plus 14 lots of 0. And so if we put that in the calculator, we get 931 over 24 meters, and that's positive, so that's great. And so that's my answer. Okay, there we are. So that's the distance from 0 until t is 7 over 2 when it changes motion. For 5 marks, okay, not too bad of a question, I don't think, there. Once you understand what the terminology means and what it means when it changes direction, once you realise that means v0, that hopefully shouldn't be too bad. Okay, we're going to finish off with this question, which I think is probably the hardest one. For not many marks either. But anyway, a particle P moves along the x-axis, and the displacement is given by x is a half of t squared of t squared minus 2t plus 1. Okay, and then in part A, it wants me to find the times when it's at rest. So again, that means v, the velocity, is 0. So again, we've got the displacement, but we need the velocity. So we're going to actually differentiate, right? So to get from displacement to velocity, it's differentiation, right? Well, to make this sort of easy to differentiate, let's expand the brackets. So this is a half of t squared is t to the 4. Then half t squared times minus 2t is minus t cubed. Then half t squared times 1 is just a half t squared. So we're just going to differentiate this here. So then v, if I differentiate, well, half t to the 4 will go to 2t cubed. Then minus t cubed will go to minus 3t squared. Then half t squared will go to just t. And there we are. So then if we want to find the times when it's at rest, so we're going to consider v0. So at v0, then we get this equation 2t cubed minus 3t squared at t equals 0. So solving this, well, we can factor a t out. So we get 2t squared minus 3t plus 1 in here. So that means either t0 or this quadratic equals 0. And so we can solve this quadratic here. Let's just use the formula. So t is going to be 3 plus or minus the root of minus 3 all squared minus 4 lots of 2 lots of 1 over 2 lots of 2. And so doing that, I get t is 1 or t is a half. Okay, so these two make sense. Okay, so we've got these 3 values. Okay, so we've got these 3 times t0 or t's 1 or t's a half. Okay, and we're given t's greater than or equal to 0, so all 3 of those solutions make sense. There we are. Then in part B, it wants me to find the total distance in the interval 0 to 2. Now you'll see where this is harsh because we've got less marks on the other question and we're going to have to do a bit more work. Okay, so we want to find the total distance between 0 and 2. Okay, so in other words, we want to consider the integral from 0 to 2, right? Because that's that's the distance we consider in between, right? 0 to 2. And we're going to integrate the velocity, because remember again, the velocity, the area underneath the velocity graph here tells me the distance. So make sure you remember that. So we're integrating velocity. So 2t cubed minus 3t squared at t. Okay, so that's ultimately what we want to work out, but we're going to need to split the integral. And we're going to need to split the integral between the times when it's at rest, which we worked out in part A, okay? So we start from 0 and then we go up to a half. That's the first time it comes to rest, right? And then we're going to go from a half up to 1, because that's the next time it goes to rest. Or when it hits the axis, right, on the velocity graph. So it might start to go underneath the graph and vice versa. And then we're going to go from 1 to 2. So we're going to need to work out 3 different integrals, right? Compared to the last question where we only had 1 for 5 marks. But yeah, okay. Again, you can do it either method. I might show the other method as well with the displacement formula. But let me do this first. So again, at this point, we split up the integral between the intermediate times where it comes to rest. So that might be when the graph goes negative. Okay, so I expect some of these integrals to be negative. So we need to make them positive when we get to it. Okay, so again, we're going to work out each individual separately. So first, between a half, from 0 to a half of 2t cubed minus 3t squared at t dt. So integrating that very quickly, we would get 2t to the 4 over 4 minus 3t cubed over 3 add t squared over 2 between a half and 0. If we simplify this, we get a half t to the 4 minus t cubed add a half t squared from a half to 0. And okay, so then we plug in our limits. So it's going to be half of a half to the 4 minus a half cubed plus a half of a half squared. And then I'm going to sub in 0. And so that will get me 1 over 32. And there we are. Okay, positive, that's great. So then we're going to work out the second integral. So that's between a half to 1 now. Of the same expression, the velocity here. Okay, so again, we don't need to manually work the integral out. We can just reuse it now. So it's a half t to the 4 minus t cubed plus a half t squared between now a half to 1. Okay, so if we plug in our new limits, do I have room here? Okay, squeeze it in there. Okay. Right, if I work that out, and hopefully you realise you don't have to write it all out, because hopefully you realise from here, the last integral, this is just going to be 1 over 32. So you can cut down on some of the calculator time by just only typing in this integral here. Okay, So this is 0 minus 3 minus 1 over 32. So it's just minus 1 over 32. Okay, that's negative. We're going to have to flip that, but that's fine. Okay, so that's the second integral. Then the third one is between 1 to 2. Okay. And I make a note that's 0. Okay, so that's again the same velocity expression. So again, we know that integrates to a half t to the 4 minus t cubed at a half t squared from 2 to 1. So if I plug in my limits, and again, I don't need to type the whole thing on the calculator because this is 0, right? I saw that previously, so I just need to type this in my calculator. And so this bracket is 2, so this is 2 take away 0, which is just 2. Okay, and so there we are. So therefore the total distance then from 0 to 2, well, we add up all these 3 individual distances. So we've got 1 over 32 from the first one, then we add minus 1 over 32, right? But then we make that positive, so it's plus 1 over 32. Then we add on the 2 at the end here. Okay, so if we do all that, we get 33 over 16 meters. And so there we are. Okay, alternatively, I will show the other method in this case because I think it's quite interesting what happens here. So alternative, right? We're going to use the displacement formula. So we already have the displacement already, I'm pretty sure. Yeah, we were given it in the question. So actually, considering how long it took for the integrals, and we already had the displacement ready for us, really, what we can essentially, you might prefer to opt for this method if you're more comfortable. But again, it's going to be tricky because again, it'll be displacement we're dealing with and things will cancel. So you have to be very careful. So again, the displacement formula is x is a half t to the 4. Minus t cubed at a half t squared. Okay, so again, what we're going to do, the exact same idea as with the integrals, we'll need to compute the velocities at 0, so the time and the velocity is 0, which we did in part A. So we've got t0, t1 and t's a half. Okay, so remember what we're going to substitute into here is we're going to sub x is 0. We're also going to sub in the other endpoint when x is 2. No, sorry, t is 2. Sorry, t is 2. Because remember, it's between 0 to 2. So we sub in our endpoints, okay, to find the displacement there. Then we also sub in the intermediate times when it comes to rest. So to a half and 1. So we've got 4 things to sub into. So it's not going to be the nicest either doing it this way, but we got no choice really. So when t's a 0, when t's 0, hopefully spot x will be 0 as well, because it will all go to 0. Then when t is 2, x is going to be half of 2 to the 4 minus 2 cubed at a half of 2 squared, which will get me 2. Okay, and then when t is a half, x will be a half of a half to the 4 minus a half cubed at a half of a half squared. Okay, so we work that out. We get 1 over 32. So again, recognise the numbers we're getting are the same. The methods are kind of the same, right? The two methods are doing the same thing, right? Really. But they're sort of presented in slightly different ways, okay? And then with t's 1, again, then x is going to be a half of 1 to the 4. And we get 0, okay, and there we are. So those are just the key values I need to consider. Now, to work out the distance I want from 0 to 2, right, the total distance travelled for the whole journey, right? So if I draw a little number line again, again, we start from the origin. That's when t is 0. Then, firstly, we go to t is a half, right? T is a half. That is 1 over 32 meters. Let's say that's over here somewhere, right? This distance is 1 over 32 meters. That's t is a half. Then, after t is a half, the next key point is when t is 1. Right, that's the next time, which is 0. So actually what happens is, it goes back to 0. So what happens is, it moves forward by 1 over 32 meters to this point, t is a half. Then after t is a half, it moves back another 1 over 32 meters backwards, and it returns to O, because it's back to 0 meters. Because remember, these are all displacements, not distances necessarily. And it returns back to 0 at t is 1. Then after t is 1, we go to t is 2, and then it goes 2 meters forward. So then it goes forward by 2 meters at the point t is 2 there. Okay, so hopefully that sort of journey applied the key distances and the key times. Hopefully that made sense how I've got to this point. So if I then compute the total distance then, so consider the whole journey. So firstly, we start here, and then as we discussed, we move forward by 1 over 32 meters. So add 1 over 32, then we move back by 1 over 32 to go back to where we start. That's, you still walked or travelled another 1 over 32 meters, right? Though, and then after that, then we move forward by 2 meters, right? So we added 2. So if we work all that out, well, actually, it turns out you get 33 over 16. And that's your distance there. So you can consider it either way. So again, you can use the integral method, which is safer, right? It pretty much, as long as you follow the method, it can't go wrong, really. As long as you compute the integrals separately and then flip any negatives to a positive, it kind of is quite secure, I'd say, right? Quite safe. But sometimes this method may be quicker, depending. But you really need to be able to visualize and plot what's going on. Okay, so if you work out all the individual displacements at each point in time, then hopefully you can draw a diagram like this, which represents all the individual distances between each point in time. Then you could add them all up. Okay, in that way. Okay, but that's not the whole question, because now we have part C, and part C is saying show that P will never move along the negative x-axis. So again, you can kind of think of this displacement here as sort of an x-axis, right? So if you have the origin here, positive x will be forwards, the negative x will be behind 0, right? So anyway, so talking about, so saying if P can never move along the negative x-axis, well, in other words, if P is never on the negative x-axis, that means x cannot be 0. No, be less than 0, sorry. That's what we want to show. Okay? But we have x here, so we need to show, in other words, if x cannot be less than 0, we need to show that x is always positive then. X is always greater than equal to 0. So in other words, we need to show that half t squared of t squared minus 2t plus 1 is always positive. Now, hopefully that rings bells to what we looked at previously, where we proved that the factors were positive or negative, right? So we've got these factors here. So if I split this up, if I split this sort of factorisation up, this is saying a half times t squared times the quadratic factor, t squared minus 2t plus 1. If I'm going to show overall it's positive, right? Well, firstly, a half is positive. T squared is positive as it's time and it's a square number. So we need to show that this is positive as well, because then positive times a positive times a positive has to give me a positive. So this is more tricky. So these two should make sense while they're positive, but this quadratic factor is a bit trickier. So how are we going to show that? You can show that multiple ways, okay? You could complete the square and show that it's show that the minimum value is above 0, so it's always positive. Maybe let's try factorising it, see what happens. So I'm going to say down here that t squared minus 2t plus 1. If I factorise that, so let's see if we can factorise it. Well, we want two numbers that multiply to get 1, positive 1, and add to get minus 2. So the factors of 1 are just 1 and 1, right? So if we want to add them to get minus 2, they both need to be negative 1, because then negative 1 times negative 1 is plus 1, and add minus 1 and minus 1 to get minus 2. So that's my factor pair. So it's going to be t minus 1 of t minus 1. Well, hang on, we can just make that squared then, because it's the same factor twice. So this is the factorisation. So alternatively, we could say, if I get rid of this then, we could say this is equivalent to a half times t squared times t minus 1 all squared. And that has to be greater than or equal to 0. So what I'm going to say then is, I'm going to say that since a half and t squared and t minus 1 squared are all positive as their square numbers, as their squares, right? Therefore, that means the whole expression, x equals a half times t squared times t minus 1 squared, is also positive. And there we are. If you want to, you could say that because a positive times a positive times a positive equals positive. That's what you want to say. So hopefully with me there. Okay, so just considered all the factors of x here, and all the factors here must be positive because they're square numbers and so forth. So the x as a whole is positive. So if it's positive, then that simply means therefore x cannot be negative. Okay, and that's really it. So therefore p cannot move on the negative x-axis. And there we are. So quite a weird question that is, quite a tricky one actually, but there we are. So hopefully that made sense there. But again, very reminiscent to some of the previous questions where we considered the factors, and we've shown that all the factors were a certain sign, so they might all be positive. So that means it's positive overall. Okay, but there we are. So that's it for this section. Again, quite an important one, I think. As you can see, like all these exam questions every year, they ask about asking for the total distance or something. So it's a key skill to learn, and I don't think it's that bad once you understand what to do. Okay, so hopefully this has gave you more confidence to tackle those questions. So again, pick whatever method you prefer, or even anything else that I haven't done in the video, but I think those are the two main methods. But yeah, I prefer the integral method. I think it's safer. I don't think you can really go wrong, although it might take a bit longer, but I don't think you can really go wrong with it once you nailed the method down. But there we are. Okay, I'll see you next time.